let's find another volume. This example is going to come from page 376 of our textbook, problem number 10. In this problem, a solid is described to us. The base of the solid is the disk, x squared plus y squared is less than or equal to 1. So this inequality telling me to take all the points on the inside of the unit circle, so shown here in blue. The cross sections by planes perpendicular to the y-axis between y equals minus 1 and y equals 1 are isosceles right triangles with one leg in the disk. So one of those triangles showed to us. At every point we'd get a little triangle that looks like that. So in the middle we get the largest triangle, so we know they're changing size as we're going through there. From the setup of the problem, I'm now perpendicular to the y-axis, so I think we're going to be integrating with respect to y here in just a moment. But let's just go on and jot some things down. I know I'm going to need to talk about a unit circle, and I'm going to draw it in a different perspective than what's on the page here. They've done a nice job of showing us a 3D perspective, make that triangle easier to understand. But I just want to talk about the stuff in the plane here for a minute. So here's my circle, x squared plus y squared equals 1. It's the disk, so I'm not going to shade it in, but I'll write what they did less than or equal to 1. All right, and I'm thinking about bases that run from one side of the circle to the other, perpendicular to the y-axis. All right, well that triangle would look like this. I'm told it's an isosceles right triangle, so this side length has to match this side length. We'll need an area function here, and our variable will be y, 1/2 the base times the height, which, well, in the notation I've adopted here is this thing times this thing, so a squared. So if I just can find what that distance is from here to here, we'll be ready to go so that we can integrate that area formula, starting at y equals minus 1 and ending at y equals positive 1. So all we have to do is figure out the area of one of those little right triangles. All right, well, base times height, I need to know this length. If I take my unit circle, x squared plus y squared equals 1, I can solve it for x. I'll get this. And this gives me a left-hand side and a right-hand side formula, right? The minus out front's talking about all of the x's that are negative. The positive out front would be talking about all of the x's that are positive. And my base runs from the left-hand side to the right-hand side. So that distance that I've called a is, well, the right function minus the left function. Or 2 times the square root of 1 minus y squared. And, well, if we think about it, half the distance over is just root 1 minus y squared, and clearly we have 2 of them. So 2 different ways to think about how to get to this formula for a. But I really need to know what 1/2 times a squared would be. So I'd have 1/2, and now I need to square this. So 4 times 1 minus y squared. So I end up with an area formula that's just 2 times 1 minus y squared. All right, so that's my nice, happy area formula for that triangle, and now we're ready to integrate. The volume we're looking for would be given by this integral. And just like in the last example video that I posted, I noticed some symmetry here, that the region is going to be generated by the same triangles on this side as in this side. So I'm going to go on and think about just finding half the volume and doubling it. So changing that lower bound just to be thinking about from 0 to 1. You could do it either way. But what I'm going to do now is pull that 2 out, and we'll find an antiderivative. All right, so 4 times, and then 1 minus 1/3 here. So I end up with a volume of 8/3. for that region described to us by our author. So whatever shape this generates, that's its volume. It's actually a nice mental exercise to try to come up with what that shape looks like in your head. So I challenge you to do that.